We're going to move on to looking at Newton's second law. So Newton's second law is F equals ma. As I say, probably the most important equation in mechanics, incredibly useful, and you need to memorize. It's not a very difficult one to memorize, but it's not given to us, so make sure you're familiar with the equation. Let's look at that car again, but this time I'm going to give you its mass. I'm going to say it weighs 1,000 kilograms. Same force as before, 2,500 Newton force from the engine, pushing it forwards, and a 1,750 Newton force backwards, mostly due to air resistance. Or you could just write drag for that to sum up all the resistances. First of all, we're going to find the resultant force again. So the resultant force is 750 newtons. But now, I want to work out what's happening to this car. If we look at our equation, we can see that if we have a resultant force, and this F, remember, has to be the resultant force, okay? You can't just pick one of these forces. I can't just say I'm going to pick that 2,500 Newton force. It must be the resultant force acting on an object. Okay, so we have to take into account all the forces acting on it. But from that, I can see that if there is a resultant force acting, there's going to be an acceleration, which is what this A is. And how much it accelerates depends on the mass of the object. Okay, so to find the acceleration of this car, I can rearrange this formula and write that acceleration is the resultant force divided by its mass, which is what I've done here. So the acceleration is the force over the mass, and remember, I'm not using this force or this force, I have to use the resultant force. So it's 750 divided by the mass of 1,000, which leaves me an acceleration of 0.75 meters per second squared. Let's have a look at another example. We're going to go back to that crane again. Same forces, it's got a mass of 500 kilograms. The weight was 4,900 newtons, which we got by using this equation. Another really important equation here, which you'll use a lot, so memorize this one as well. And we know there's 5,000 newtons, and that's the tension in the cable. That left us a resultant force of 100 newtons upwards. Okay, so the resultant force points upwards, it's 100 newtons. If we have a look at our equation, if the resultant force is 100 newtons, there's going to be an acceleration. And if the resultant force points upwards, the acceleration must point upwards as well. So it's actually accelerating upwards, this ball. It's being lifted up and it's accelerating it faster and faster as it's lifted up. Again, to find the acceleration, I just rearrange the equation and I do the resultant force divided by the mass. That's what I've done here. The resultant force was 100. Mass was 500. And that leaves us with 0.2 meters per second squared. So a very steady acceleration, which is what you'd want if you were lifting up a 500 kilogram wrecking ball. Another example, a little bit more complicated one. This time we've got a car towing another car. So this is supposed to be like a tow bar or a tow rope. We've got a big car weighing 1,000 kilograms and a little car weighing 600 kilograms. And let's mark some forces on. Let's say the front car, which is towing the second car, is providing a force of 3,000 newtons from its engine. Each of the cars has its own resistance. So this car's got some resistance. And because it's bigger, it provides more resistance than this car, for which there's a lot less resistance. Okay. Now, we want to find out if this car is accelerating or decelerating, what's happening to it. Okay, and to do that, we're going to use Newton's second law, F equals ma. Now, I've put that box around just to show us what forces we're taking account of. We're looking at this whole system as a whole, so at the moment, we're not looking at this tow rope. That has some forces in, but it's in the middle of our system. We're only looking at the forces acting on, the external forces acting on the cars. This is a force inside the system. We can look at that, and we'll do that in just a second. So we need to figure out the resultant force. This is the resultant force here. We've got the 3,000 newtons from the engine, subtract the 1,500 in resistance from the first car, and the 700 in resistance from the second car, leaves us with an 800 newton resultant force, and that goes forwards, doesn't it? Yeah. Because there's a resultant force forward, we know actually from F equals ma that there's going to be an acceleration as well. Okay, and the acceleration is going to be forward, so this two-car combination is accelerating. To figure out the acceleration, we rearrange F equals ma and do the resultant force divided by the total mass. So remember here, the mass we use in F equals ma has to be the total of the entire system. So it's 600 plus 1,000, which is 1,600 kilos. Okay, we have to use the full mass of the combination. And that gives us an answer of 0.5 meters per second squared, which is a fairly steady acceleration. We're going to have a look at that same problem again, but now we're going to focus in on that tow rope. So same car, same mass, but this time we're going to focus on that car so we can look at the tension in the cable. By changing our box to this, we're now looking just at this car, and that tension is an external force acting on that first car. So let's mark all the forces on. That 3,000 Newton force still applies from the engine. There's a 1,500 Newton force, which was the resistance from the first car. The resistance from the second car is outside the box, so we don't look at that one. And there's tension in the cable, which we'll just call T for now. And that is what we're trying to figure out. So first of all, let's figure out the resultant force, and we'll use Newton's second law in a second. So the resultant force is going to be the 3,000 from the engine minus the 1,500 minus the tension, because the tension actually points backwards. It's effectively pulling that car back. It's providing an extra load on the car. Hence the car has to work harder to accelerate at the same rate. So we found the resultant force, but we've got an unknown here because we don't know what the tension is, T for tension. But we do know that from the previous analysis we just did, we found that the acceleration of the cars was 0.5 meters per second squared. Now the acceleration has to be the same for both cars, doesn't it? Because they can't separate out because one's towing the other. So this acceleration applies to the first car, the second car, and the two-car combination. So we can use this in our equation. So if we have a look at the first line of this, we're going to use F equals ma, Newton's second law. Now I've substituted in the resultant force, 3,000 minus 1,500 minus T. I've just substituted that in for the resultant force. Equals 1,000, which is the mass. So this is the resultant force, all this bit. This is the mass, and this was the acceleration we found in the previous part. By doing a little bit of rearranging, so I'll just show you what I've done there. I've looked at the resultant force and said 3,000 minus 1,500 is 1,500. So I'm left with 1,500 minus T equals 1,000 times 0.5 is 500. And then I do a bit of rearranging, bring T to the other side, bring 500 across. And that gives me T is 1,000 newtons. Okay, so because I already know the acceleration, I can actually figure out what this force is. So as well as figuring out accelerations, we can also figure out missing forces from the resultant force, or that form the resultant force, if we know the acceleration and the mass. Notice that we've only used a mass of 1,000 kilograms here because we're only looking at the first car. Okay, so the mass is just 1,000 kilograms because our box is just around the first car. In the first section, the box is around both the cars, so we have to consider the mass of both of them put together.